distributions. Hmm. So how you guys are doing? Okay, today I did not open. Mm-hmm. Am I audible?
Yes, sir.
Yes, sir.
Good evening, good evening, good evening, good evening. Good evening. Okay, so we enter into chapter number 2, probability distributions. Now, what exactly is a probability distribution? I'm pretty sure all of you have heard about this word called probability distribution. When you say probability distribution, what is the meaning of this so-called distribution? Before we go ahead and that are specifically in our scope of syllabus, it would be better if we, first of all, try to understand the probability distribution itself. So let's start with understanding probability distribution first. The very first topic we are going to dedicate to build just an understanding of probability distribution. That what exactly probability distribution is. Okay, so we are going to build some understanding of probability distributions. And to build an understanding of probability distributions, we will start with a problem. We'll start right at the start of the chapter, we start with a problem. Yes, right at the start of the chapter, we start with a problem. And the problem goes like this, that suppose we are rolling a die. Suppose this is the random experiment, and the random experiment is that we are rolling a die. Now, the event in which I'm interested is not the number that the die turns up. I mean, sometimes you say, "Now, what is the probability of getting 1? What is the probability of getting 2? What is the probability of getting 3? What is the probability of getting 4? What is the probability of getting 5? What is the probability of getting 6? That's not we are interested in. We are interested in the number of rolls that we need to do until the first time a given number, let's say 1, appears. We are interested in how many rolls need to be done at least once for the first time, 1 appears, or 2 appears, or 3 appears, any one number you can take. So we are interested in this kind of an event. The event that we are interested in is number of the event that we are interested in is the number of roles. Number of roles till 4 appears for the first time. So how many rows you are doing till 4 years for the first time? Now, what is the probability 4 in one row is 1 upon 6. And what is the probability of not getting 4 in a given row? In a given roll of the die, the probability of not getting 4 is going to be 1 minus 1 upon 6. 1 minus 1 upon 6, that becomes 5 upon 6. So this is the number of rolls till a 4 appears for the first time. So what's the answer that this event is going to have? The answer that this event is going to have is either 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10, because the number that appears on the die is not really the event. That's not the event. The event is how many times we are rolling the die. So we can keep rolling the die 50 times. There is no upper limit of 6 here. In a die, you have only 6 numbers, but here your event can be designated as a success after 50 number of rolls. So it is important to understand that you might get success in the very first attempt. In the very first attempt, I'm just representing that number of attempts as capital X. So you might get success in the very first attempt. That means you might get 4 right in the first attempt, and getting 4 right in the first attempt is having a probability of 1 upon 6. That is 0.167. But you might get success not in the first attempt, but rather in the second attempt. First time you roll the die and a 4 doesn't appear. And second time you roll the die and 4 appears. First time you roll the die and 4 doesn't appear. And second time you roll the die and 4 appears. This is again a way to succeed. So first time there is an and here. And means that you are performing multiple random experiments or multiple trials of a random experiment. It becomes a compound random experiment. So first time you don't get a 4, and then the second time you get a 4. I can even ignore decimal values, and let's just go ahead with 1 upon 6, and second one 5 upon 6 into 1 upon 6. But if I ask you that what is the probability that x will be equal to 3? X is what? X is the number of attempts or number of rolls till 4 appears for the first time. Let's call it number of attempts. So number of attempts, you keep rolling the die till 4 appears for the very first time. Now, if you are saying that 4 appears in the third attempt, that means 4 doesn't appear in the first attempt, and then again 4 doesn't appear in the first attempt, and then again 4 appears in the third attempt. Now, what is the probability that we are going to have here? Probability that we are going to have here is 5 by 6. No success in the first attempt. 5 by 6 again, no success in the second attempt, and 1 upon 6, we get a success in the third attempt. We get a success in the third attempt. Now, if I ask you, x is equal to 4, what is the probability of getting success in the fourth attempt? Getting success in the fourth attempt, probability is going to be, you don't get a success in first attempt, and then you don't get success in second attempt as well, and you don't get a success in third attempt, and you get success in the fourth attempt. It's very clear that this time you are going to have 5 upon 6 power 3 and multiplied by 1 upon 6. And this one will become 5 upon 6 power 2, 5 upon 6 power 2 multiplied by 1 upon 6. Similarly, what is the probability of x becoming equal to 5? What is the probability of x becoming equal to 5? The probability of x becoming equal to 5. Ramanujan, how you are doing? The probability of what is the probability of x becoming equal to 5? It doesn't mean that a 5 appears on dice. It means that we get a success after fifth attempt, after fourth attempt. We get the success in fifth attempt. Okay, so we don't get a success in first attempt, and then again we don't get a success in second attempt, and then again we don't get a success in third attempt, and then again we don't get a success in fourth attempt, and then again we get a success finally in fifth attempt. It's very clear that this time you are going to get 5 by 6 power 4 multiplied by 1 upon 6. Similarly, if I calculate what is the probability that you get success in rth attempt, you get the success in rth attempt or xth attempt. Many books actually use R, but I think the very idea of probability distribution gets more fun when you use X to represent any general value of capital X. Any general value of capital X. So that means you don't get success. You get no 4 in the first attempt, 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 and finally, you get a 4 in the last attempt. Which means out of X attempts you performed, X minus 1 attempts, there is no success. And last attempt, that is the attempt number X, you get a success. So X minus 1 attempts go blank, X minus 1 attempts go black, X minus 1 attempts, you don't get a success, and you get finally the success in just the last attempt. So you are going to get 5 upon 6 power, how many times? 5 upon 6 power X minus 1 multiplied by 1 upon 6. If I say 5 upon 6 as the probability of, if I say probability of success as a small p, then probability of failure will become 1 minus 1 upon 6. So I can write it 1 minus p. So I can very clearly take a general form here, and that general form is going to be, so let's take a general form, and if I generalize this result, that generalized result is going to look like p power 1 minus p power x minus 1 multiplied by p. So that generalized result will look like this. Small p power, the generalized result looks like this, that the probability of capital X becoming equal to small x, that means I'm going to get success in X attempts. The probability of doing this, my dear friends, is how much? That probability is 1 minus p power 1 minus p power x minus 1, and finally multiplied by small p. And then it is multiplied by small p. Cool. Now you notice that So far in chapter number 1, ध्यान से समझियो. In chapter number 1, when you defined probability, you said probability of an event. Here, your language is a little bit changed. You say probability of X becoming 1, probability of X becoming 2, probability of X becoming 3, probability of X becoming 4, probability of X becoming 5. In chapter 1, the whole chapter, your language, your understanding of probability was always the probability of an event. Now, your language is a little bit changed. Now you don't say probability of an event. Now you are saying probability of X becoming 1. Now you are saying probability of X becoming 2. Now you are saying probability of X becoming 3. Now you are saying probability of X becoming equal to some number. X, my dear friends, X, my dear friends, whose value can become 1, whose value can also become 1, can also become 2, whose value can also become 3, whose value can be 4, whose value can be 5, 6, 7, 8, anything that X, which can take any random value, whose value is not fixed, whose value is, which value it is going to take, that's not sure, that's not certain. That X, whose value is not fixed, that X is known by the name random variable. So far, you said the similar thing by the name event. Now you are going to convey your event in the form of capital X. Capital X will take a value and then something will happen. Capital X will take equal to 2. That means you got the success in 2 attempts. So you say your language has changed only. You say getting success in first roll, getting a 4 in the first roll or first attempt of rolling a die, that is like probability of an event. You say probability of X becoming 1, that's the probability of a random variable. So random, we generally assign some kind of random variable to an event, but there is a difference here. Event can be subjective. Event can have characters like alpha, beta, gamma. Event can have letters, alphabets, sentences becoming reality. But random variable is always going to have some numerical value. For example, you think about a coin. In case of coin, you don't have any number turning up, but I can always convert the whole thing into quantitative model. How I can convert the whole thing into quantitative model? When you toss a coin, do you have any number turning up? So how do you say that a random variable can only attain some numerical value, not some character? When you toss a coin, you either get a head or get a tail. But I can always define an event or a random variable such that it will have quantitative value. For example, suppose we are tossing the coin 10 times. Suppose we are tossing the coin. We are tossing the coin 10 times. And if we are tossing the coin 10 times, suppose I want to calculate probability of getting at least 6 heads out of 10 tosses. So out of 10 tosses, I want to calculate the probability of at least 6 heads. So I'm going to define a corresponding random variable, and that random variable is the number of heads. I will define a corresponding random variable, and that random variable is the number of heads. Number of heads in 10 tosses. Out of 10 tosses, how many heads are you getting? Now you see, the random experiment doesn't involve any number. It involves characters. It involves symbols, head and tail, H and T. And you're tossing the coin 10 times, and I want to calculate the probability of at least 6 heads. Then I define a corresponding random variable, number of heads in 10 tosses. Number of heads in 10 tosses. And now I convert this objective. What is the objective here? Objective is getting at least 6 heads. Now I convert this whole objective in the language of a random variable. Now I convert this whole objective probability of getting at least 6 heads in the language of my random variable. And if I convert this into the language of my random variable, I'm going to say at least 6 heads means what? At least 6 heads means that I get 6 heads, then also I'm satisfied. Or if I get 7 heads, then also I'm satisfied. Or if I get 8 heads, then also I'm satisfied. Or if I get 9 heads, then also I'm satisfied. Or if I get 10 heads, then also I'm satisfied. So if I get 6, 7, 8, 9, or 10, anything, I'm satisfied. In very short, I write this whole thing. In very short, I write this whole thing in the language of a random variable, that my random variable must be equal to or more than 6. Naturally, the maximum value is 10 because I'm tossing the coin maximum 10 times. So basically, there is something given in terms of the language you studied in previous chapter. And then there is something we are doing in terms of the language we are introducing now. The language of events you studied in the previous chapter. In this chapter, you will have to get habituated to the language of random variables. We are only converting, we are only changing the language, we are only changing the way we call probabilities. In the previous chapter, we would have said probability of at least 6 heads. In this chapter, we will say probability of X becoming greater than or equal to 6. They both represent the same thing. But mathematics always likes being more precise and defining things in terms of some quantifiable variables. So now we can at least 6 heads is not a very mathematical way, but X greater than or equal to 6 seems all of a sudden like a mathematical way to express something. Cool. So this is how we convert the language of an event into the language of a random variable. Into the language of a random variable. My dear friends, defining a random variable corresponding to, so you understand the difference? Event can be subjective, event can be written in terms of a statement, but a random variable is always going to have some numerical value, even if you are tossing a coin. Coin doesn't have any number, but still you can define a random variable such that it will have some numerical values. For example, you might get just 1 head out of 10 tosses, or you might get 5 heads out of 10 tosses, or you might get today also watching the class while traveling, following you yesterday's advice. That's great. You can actually maximize your traveling productivity. You're traveling also, so that's one thing you are achieving, and at the same time you are learning also. So second thing you are achieving. So basically, ek panth do kaj. So an event can always be translated in the language of, an event can always be translated in the language of a random variable. Mind it. Now we are going to have our attention back to our current project. And the current project was, now we will have our attention back to our current project. Okay, this is creating some So let's have our attention back to our current project. Our current project was that what's if I'm rolling a die, what is the number of attempts I do till the 4 appears for the first time? Till 4 appears for the first time, and we say p we get 1 minus p power 1, and into p we get 1 minus p power 2 into p, 1 minus p power 3 into p, 1 minus p power 4 into p, 1 minus p power x minus 1 into p. We have a general identifiable pattern. My dear friends, we have actually done nothing but use the multiplication law of probability to achieve all these values. To achieve all these values, we have simply used the multiplication law of probability. But you notice that now I can represent all these things. Like I can represent x getting 1, and then x getting 2, and then x getting 3, and then x getting 4, and then x becoming small x. And I can also write the corresponding probability values. The corresponding probability values are 1 upon 6, and then we have 5 upon 6 multiplied by 1 upon 6, and then we have 5 upon 6 square multiplied by 1 upon 6, and then finally we have 5 upon 6 power x minus 1, 5 upon 6 power x minus 1 multiplied by 1 upon 6 multiplied by 1 upon 6. Cool. So we can actually create a table, and we can tabulate all the values of x, and we can go ahead and tabulate all the corresponding probability values. When x is becoming 1, what is that probability? When x is becoming 2, what is that probability? When x is becoming 3, what is that probability? When x is becoming equal to small x, what is that probability? Okay, this in a tabulated way, we can represent this whole spectrum of x values, and also we can represent the corresponding probability values. But frankly speaking, this is not the only way to represent the relationship between the random variable capital X and the probability values capital P. This is just one way to create a table in which the random variable 1 and the corresponding probability. The random variable is becoming equal to 2 and the corresponding probability. Random variable becoming equal to 3 and corresponding probability. Random variable becoming equal to x and corresponding probability. But this is not the only way to do this. We have one more way to do this. And that way is that just like ordinary calculus, we can always go ahead and we can plot all these values by taking random variable values plotted along horizontal axis and probability values plotted along vertical axis. So probability of x becoming 1 is known to me, and that value is 0.167. That value I know 0.167. And then there is probability of x becoming 2. Probability of x becoming 2 will become 5 upon 36, and 5 upon 36 is 0.222, 5 upon 36. 0.138. So this is a little less value, and this value is 0.139. And then x becoming random variable becoming equal to 3, that value will become 5 upon 36 and further divided by 6 and multiplied by 5. This is 0.116. This probability value is 0.116. Similarly, x becoming equal to 4, random variable becoming equal to 4, and the corresponding probability value will be 125 upon 6 power 4. 125 upon 6 power 4, this is even less than 0.1. This becomes 0.096. 0.096. It's a general practice to represent, because probability is plotted along the vertical axis. It's a general practice to represent these values by the height of this diagram. So basically, we are creating a histogram. We are creating a histogram where each height of each column is representing the Height of each column is representing the probability of one certain x value, one certain value of random variable. But there is one more way we can represent, like tabulating everything, one particular value of x and corresponding probability, 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 or plotting all these values is still a laborious way. It's still a laborious way. So we can actually do all this most of the times in a very short manner by simply expressing a mathematical function that will generate all the values, all the values, all the values, all the values that you have tabulated, or all the values that you have plotted. My dear friends, I can simply represent 1 minus p power 1 minus p power x minus 1 multiplied by p. 1 minus p power x minus 1 multiplied by p. This makes our job easy. Next time I'm going to calculate the probability of getting success in third attempt, I will not do this. I will simply use the formula. Next time I'm going to calculate the probability of getting success in 5 attempts, I will not express that event being satisfied by this event and this event and this event and this event and this event, and then using the multiplication law, I will simply use this formula to calculate the probability of getting success in 5th attempt. My dear friends, whether you tabulate or you plot or you express it as a function, whether you express it in the table form or you express it in the form of a histogram, in the form of a plot, or you express it in the form of a mathematical function, all of them all of them are simply the functions, simply a mathematical function that can, for any input value of random variable, treat random variable like you treat input in calculus. You treat x comma y, no? X horizontal axis, y vertical axis. Similarly, you treat random variable as an input, and a probability distribution is nothing but a function that can generate probability values corresponding to any x value. A probability distribution is nothing but a function that can generate probability corresponding to different values of random variable. I repeat for one last time, a probability distribution is nothing but a function that either you express that function in the form of a table, or you express that function in the form of a plot, or you express that function in the form of a mathematical function. Its job is to give you the output values, where output is probability here, corresponding to the input values, where input is the random variable. My dear friends, these three ways exist. This is one way, this is another way, this is another way. Because it seems like, just like you study y is equal to e power x, y is equal to sine x, mathematical functions, for any x value, they can generate y value. For any x value, they can generate corresponding y value. Because these also look like them, people named this probability mass function. Why mass function? Probability also having mass? No, there is a logic, there is a reason why people called it probability, not simply probability function, but why people called it probability mass function. But that you will be able to understand only after understanding continuous distributions. So these are the three different ways of expressing a probability mass function. So what is a random variable? Random variable is defined for an event such that it can only take numerical values. It can only take numerical values. It can take both positive, negative, both kind of values, but most of the times it will take positive values. But random variables can be defined in such ways that their even negative values will be possible. I'm not saying probability negative will be possible. I'm saying random variable becoming some negative number would be possible. I'm never saying probability negative will be possible. No, I'm saying random variable becoming equal to -1 will be possible. Random variable can have decimal values, can have integer values, can have positive, negative, any kind of values. Random variable is a general term for defining an event. And then what is a probability distribution or probability mass function? Probability distribution or probability mass function is either a function expressed in the form of a table, or a function expressed in the form of a plot, or a function expressed mathematically as a mathematical relation that gives you the probability values corresponding to all possible values of random variable. I hope this one problem, this one illustration must be helping you build the concept of what probability distribution is. I hope that you have now started understanding a little bit that it's like a function, it's like a box where random variable is an input and probability values are the outputs. I feed x is equal to 1, probability value is given as an output. I feed x is equal to 3, probability value. So it's a simple box, it's a simple machine. Probability mass function or probability distribution is a simple machine, Probability mass function is just like a machine where ganna dalo, juice nikalo. Okay, where you input random variable values and you get probability values. Where you feed the sugarcane and you get the juice of sugarcane stick out. All right, so this is how you understand probability distribution. Now we go ahead and start, build our strength more on this. So let's just take one more similar example. But before I take similar example, let's try to answer a question regarding this event. If I'm defining the random experiment, number of attempts till 4 appears for the first time, till 4 appears for the first time, what is the probability of x is equal to 10? Now, probability of x is equal to 10 means what? Probability of x is equal to 10 means you get 4 appears in 10th attempt. 4 appears in 10th attempt. All right. So 4 appears in 10th attempt. One way to do this. That 4 doesn't appear, and 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 4 doesn't appear. 1, 2, 3, 4, 5, 6, 7, 8, 9, and finally 4 appears. Because all of them are separated by and, I write 4 doesn't appear, and then 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 again 4 doesn't appear. 4 doesn't appear, 1, 2, 3, 4, 5, 6, 7, 8, and 4 doesn't appear, and finally a 4 appears. This is one way. Another way is simply use the formula. once you understand that, oh, I know this kind of problems fit into this formula, I know this kind of problems fit into this formula. So if I know this kind of problem fit into this formula, I simply go ahead and do this. X is equal to 10, and x is equal to 10 means that I'm going to have 1 minus 1 upon 6 power 9 multiplied by 1 upon 6. That gives me exactly the same answer, but with lesser efforts. That gives me exactly the same answer, but with less effort. Cool. So this is how probability distribution can benefit. Now I take one more similar example. Let's take one more similar example. Let's say there is a salesperson. I'm going to take another example, and that one is again similar. So let's say we have a salesperson, and that salesperson is trying to sell a product. A salesperson is trying to sell a product to people in marketplace, and probability of any given person agreeing to buy the product probability of any given person agreeing to buy the product is given to you, and that is only 0.15. Only 15% chances are that the person is going to agree to buy the product. Naturally, what will be the probability of a person not willing to buy the product? What is the probability of a person not willing to buy the product? A person not willing to buy the product, this probability will very clearly, this probability would be 1 minus p, which is 1 minus 0.15, which is 0.85. Now, what is the probability that he will get success in first attempt? The probability of getting, I'm going to define now a random variable. Surrounding this whole problem, now we define a random variable, and that random variable should have a very clear-cut definition, okay? We define a random variable here. Just like in the same random experiment, there are multiple ways to define the events. Similarly, in a given random experiment, there are multiple ways to define the random variables. For example, here I can define a random variable in two altogether different ways. One is defining a random variable as the number of customers asked before the first agrees to buy the product. Another way to define the random variable is that if I ask 10 people, number of people who agreed to buy the product, and both are differently defined random variables. One way to define the random variable is that how many persons I'm going to ask before one person finally agrees to buy my product. Another way to define the random variable is that I'm not interested in the number of attempts before first person agrees to buy the product. I'm actually going to ask 10 people, and I'm interested in how many out of those 10 people. Let's say, what is the probability of 4 persons agreeing out of those 10 people? Now that's a different random variable. By the way, we define a random variable here as the number of attempts Still, first person agrees to buy the product. Number of attempts till the first person agrees to buy the product. So how many attempts I need to make? So maybe this X value, the random variable that has been defined in this way, if you define a random variable in this way and you call it capital X, now what is the value that this capital X can have? The value that this capital X can have is X is equal to 1. Maybe you get the very first person agreeing to buy your product, and you get the very first person to buy your product. What will be the probability of that? Probability of that will be 0.15. But maybe that the first person, maybe the second person is going to agree to buy your product. So if the second person is going to agree to buy your product, naturally the first person did not buy. The first person did not buy not. And then you ask the second person and he says, yes, I will buy. Now, this is very clearly going to be 0.85 multiplied by 0.15. And then, my dear friends, there is random variable can also take value 3. Random variable can also take value 3. And what is the probability of random variable taking a value 3? Random variable taking a value 3, probability will be that don't buy, don't buy, don't buy, don't buy, and then don't buy again, and don't buy again, and finally you have third person agreeing to buy the product. You have third person agreeing to buy the product. So 0.85 multiplied by 0.85 multiplied by 0.15. Once again, I can calculate, I can keep calculating, but you now understand we can generalize. What is the probability of capital X becoming equal to small x? This means first person doesn't buy, and then second person doesn't buy, and then third person doesn't buy, and then fourth person doesn't buy, and finally the xth person agrees to buy the product. So X minus 1 people, X minus 1 persons refuse to buy the product, and finally xth person buys the product. Naturally, you are going to have 0.85 multiplied X minus 1 times, and finally 0.15 multiplied once. Once again, my dear friends, you have the same 3 ways to convey this entire information: X becoming equal to 1, X becoming equal to 2, X becoming equal to 3, and X becoming equal to any X. So corresponding probability values will be 0.15, and then 0.15 multiplied by 0.85, 0.15 multiplied by 0.85, this is 0.1275. This is 0.1275 multiplied by 0.85. Again, this is 0.108375, 0.108375. And then we are going to have a small x. So here we have a general thing, and that is 0.85 power x minus 1 multiplied by 0.15. But you can also plot this. You can also convey this whole information in terms of a plot. So 0.85 power x minus 1 multiplied by 0.15. But as I said, you can also convey this whole thing in terms of a plot where random variable values are represented along x-axis and probability values are represented along y-axis, x becoming equal to 1. The corresponding probability is 0.15, x becoming equal to 2. The corresponding probability value is 0.1275, x becoming equal to 3. The corresponding probability value is 0.108, x becoming equal to 4, x becoming equal to 5. You can keep calculating all these probability values. But there is one and probably the best way to do this. That best way to do this is just to express that whole thing in terms of general value of random variable. My dear friends, once again, I'm repeating the same thing, that probability distribution is simply a machine. Probability distribution is simply a function, either expressed in the form of a table or expressed in the form of a table or expressed in the form of a chart or expressed in the form of a mathematical function, such that it can keep generating the probability values corresponding to different values of a random variable. Random variable is an input, and probability distribution or probability mass function simply gives you output in the form of probability. Just like normal functions you study in mathematics, y is equal to 5x plus 3, y is equal to 2x power 5 plus 9x power 4 plus 3x cubed plus 2x square minus 10. Y is equal to sine square x minus cos x. Y is equal to e power x. Y is equal to log x. Just like the functions you study in ordinary calculus. Similarly, you have a function arising here in probability distributions that can keep giving you the probability values corresponding to the values of random variable. Random variable becomes 1, probability value. Random variable 2, corresponding probability value. Random variable 3, corresponding probability value. Random variable x, corresponding probability value. Then you are going to have same thing conveyed in the form of a chart, same thing conveyed in the form of mathematical function. I hope now you have got an idea that probability distribution is nothing but simply a function that can keep generating the probability values corresponding to different values of a random variable. All right, so like suppose in this problem I ask you that what is the probability that this person will get success? What is the probability that this person will get success in at least 5 attempts? What is the probability that this person will get success in at least 5 attempts? How would you calculate it? This was the demonstration. Now I ask the main question. And the main question is, can you calculate the probability of this salesperson getting success? That means successfully selling the product in at least 5 attempts. What's the probability? Can we calculate? Let's do it. What's the probability of this person, this salesperson, getting success in 5 attempts? Can you change this probability problem in terms of, in the language of random variable? What is the probability of getting success in at least 5 attempts? What's this probability? That means in 5 attempts you can get success, or in 6 attempts you can get success, or in 7 attempts you can get success, or in 8 attempts you can get success, or in 9 attempts you can get success, or in 1,000 attempts you can get success. You agree? I have translated the given problem in the language of random variable in a very neat manner. At least 5 attempts means what? That maybe you get success in 5 attempts, or at least means more than that. So maybe you get success in 6 attempts, maybe you get success in 7 attempts, maybe you get success in 8 attempts, you get success in 9 attempts, like that. So if you really go ahead and try calculating this, this is going to be a big problem. I mean, now you need to apply additional law of probability first, and you need to break these values like P, probability of X is equal to 5, and then probability of X is equal to 6, and then probability of X is equal to 7, and then probability of X is equal to 8, and then probability of X is equal to 9, and then probability of X is equal to 10, blah, 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 blah. We, rather than following this, we are going to say that probability of X becoming 1, or probability of X becoming 2, or probability of X becoming infinity. If I add all these probabilities, naturally he will get success in from 1 to infinity, he'll get success. That's a certain event, actually. That's a certain event. X is equal to 1 or X is equal to 2. Basically, we are covering whole sample space. Whole sample space means the entire domain of random variable values. So we are covering entire domain of random variable values. So this total probability must be 1. And this total probability must be 1. And I'm interested in all the values after X is equal to 5. Then if I'm interested in all the values of X becoming equal to or greater than 5, I can take the probability of X becoming less than 5 to right hand side. And this time I don't need to sum up in finite terms. I just need to sum up 4 terms. And I'm not even going to calculate them in ordinary law, applying multiplication law of probability. I'm going to calculate them using my probability distribution formula. Now I know X less than 5 can be satisfied either by X is equal to 1, or by X is equal to 2, or by X is equal to 3, or by X is equal to, or by X is equal to 4. And I'm going to use, as I said, my probability distribution formula, and that probability distribution formula is 0.85 power X minus 1 multiplied by 0.15, 0.85 power X minus 1 multiplied by 0.15, and then 0.85 power X minus 1 multiplied by 0.15, and then again 0.85 power X minus 1 multiplied by 0.15. Add all these values and report the final answer. So 0.85 into 0.85 plus
0.7125, sir.
0.72?
0.7125.
0.7125. That becomes the final answer. So probability distribution, saying it one last time, probability distribution or probability mass function is a function that can keep generating the probability values. The probability mass function or the probability distribution that you studied just now through 2 problems is, because my dear friends, its general definition is 1 minus p power x minus 1 multiplied by small p. Its general definition is 1 minus p power x minus 1 multiplied by small p. If I calculate probability corresponding to x is equal to 1, I get 1 minus p power 0 into p. If I calculate the probability of x becoming equal to 2, I get 1 minus p power 1 into p. If I calculate the probability of x becoming equal to 3, I get 1 minus p square into p. If I calculate the probability of x becoming equal to 4, I get 1 minus p cube multiplied by p. If I calculate probability of x becoming equal to 5, I get 1 minus p power 4 into p. If I calculate the probability of x becoming 6, I get 1 minus p power 5 into p. It's very clear following something. Each subsequent term of this function, each subsequent output value of this function is very clearly following something. That we have something and then power becoming from 0 to 1 to 2 to 3 to 4 to 5. This is very clearly a, and then a multiplied by r power 1, and then a multiplied by r power 2, and then a multiplied by r power 3, and then a multiplied by r power 4, and then a multiplied by r power 5. This, my dear friends, is a geometric progression, because the probability values corresponding to different random variable values form a geometric progression. The distribution defined by this probability mass function is called by the name, is popularly known by the name geometric distribution. The probability distribution defined by this probability mass function, the probability distribution defined by this probability mass function, by probability mass function, by this probability mass function, which is defined by equation number 1, is known as geometric distribution. Okay. And since we have changed the language of conveying probability now, we have started conveying probability in a different language now, in the language of variables, in the language of functions. We have started calling probability functions, and we have started calling events as random variables, and probability values as probability functions. My dear friends, it's very clear that we need to revisit the 3 axioms of probability, and we need to redefine them in the language, in the new language that we understand now. Since we have discovered a new language of expressing probability, we have started talking not in terms of events, but in terms of random variable and its values. We've started talking not in terms of probability of a single event, but we have started talking in terms of probability mass function, which can keep giving me the output values as probability values corresponding to different values of input random variable. So we have discovered a new language, a new way to understand, to read, to study, to write, to analyze probabilities. And therefore, our 3 axioms need to be revisited. Let's revisit our 3 axioms. And let's translate our 3 axioms in terms of our new language, our new way to discover and discuss probabilities. So there is an altogether new tariqa, new way new methodology to understand, to study, to do the analysis of probabilities. This was the very first thing. And we started understanding the very first thing we understood what is a random variable. Random variable is something whose values are not certain. Random variable is something whose values are not certain. And my dear friends, second thing, random variable can take numerical values only. It can be quantified. For example, name of the city can never become a random variable. It doesn't have a quantity, doesn't have a numerical value. But the number of cities can be used as a random variable. Number of cities I visited this year, it's a random variable. Maybe I visited 2, maybe I visited 3, maybe I visited 4, maybe I visited 5. Second thing that we understand is what is a probability mass function. Probability mass function, my dear friends, probability mass function can be expressed in 3 alternative ways. One way is expressing it as a general function, that 1 minus p power, like this is just one possibility that we have discussed so far. Or we can express probability mass function in terms of a plot. X becoming equal to 1 has certain probability, x becoming equal to 2 has again certain probability, x becoming equal to 3 again has certain probability, x becoming equal to 4 again has certain probability, x becoming equal to 5 again has certain probability. And my dear friends, another way is that we are going to create a table, x taking up the value 1, and then there is a corresponding probability, let's say 0.1, and then x becoming equal to 2, and we again have corresponding probability, let's say 0.09, and x becoming equal to 3, we again have certain probability, let's say 0.9 into 0.1, which is 0.081. 0.081, x becoming equal to 4, again we have 0.0729, 0.0729, x becoming equal to 5, again we have 0.06561, 0.06561. All right, so we can keep expressing x values and corresponding probability values, and we can express all these values in the form of a table. All these values can be expressed in the form of a table. Cool. We can keep expressing in the form of a table. This is called probability mass function. We call it probability mass function. Now is the time to re-express, because we have started talking events in the form of random variables, and we have started talking probability values in the form of probability mass functions. Either you express it in the form of a table, or you express it in the form of a chart or plot, or you express it in the form of a mathematical function. It's the time to revisit our 3 axioms. What are the 3 axioms? You remember? You remember the 3 axioms. Somebody please come forward and tell me what are the 3 axioms that we understood in chapter number 1.
Probability
of event is not negative, sir.
So Three axioms revisited. What was the first axiom?
Probability greater than zero, greater than equal to greater than zero, sir.
So can you tell me how would you write this same axiom in new language? Probability of an event can never be negative. Probability of an event is always going to be positive because an event, worst case, it will not happen. It will have zero chances of happening. So can you express this axiom number 1 in our new language?
Sir, probability not less than equal to zero.
No. In our new language is the language of random variables and the language of probability mass functions. Our new language is the language of random variables, that we convert any event in corresponding
Probability
random
of
variables.
x greater than or equal to 0, sir.
Probability of random variable taking any general value will always be positive. That becomes axiom number 1. Now, what was the second axiom? Somebody come forward and tell me what was the second axiom of probability.
Probability of whole sample space is 1.
The probability of whole sample space means covering every possibility. Probability of whole sample space is 1. Can you convert this axiom in our new language, in our new methodology of dealing with probability? We are actually doing nothing. We are just, previous chapter we dedicated to learn probability. We are just inventing a new methodology to deal with probabilities. That means we are defining some functions that can take some random variable input values and give probability as the output values. These functions can be expressed either in the form of a table or in the form of a plot, or they can also be expressed in the form of a simple mathematical relation. So can you convert this second axiom in our new methodology?
Sir, probability x equal to 1 plus x equal to 2 is x equal to 1.
Probability of x is equal to 1 plus probability of x is equal to 2 plus probability of x becoming 3 plus probability of x becoming 4 ... is equal to 1.
Yes, sir.
Quite correct. Perfect. But there is a concise way to say that. Probability of x becoming any value, but since I want to cover all possibilities, naturally I'm going to sum up all the possibilities of random variable taking any value between minus infinity to plus infinity is equal to 1. Now, sometimes people see all this and they get scared that, Bapre, what the hell is this? This is actually the same thing. Second axiom. The problem is that most of the resources don't ever teach axioms. Most of the resources just start teaching probability as favorable number of elements upon total number of elements. If somebody understands the axioms, then this rule that I have written here doesn't look surprising anymore. Then the rule that I have written here doesn't look surprising anymore. My dear friends, the third axiom, if you remember, the third axiom was probability of A union B, union C, union D, union E, union F can be written as probability of A plus probability of B plus probability of C plus probability of D. Can you express that axiom number 3 in terms of the new methodology we have discovered today, we have started understanding probabilities, reading probabilities, studying and doing the analysis of probabilities in a new methodology, in a new tariqa, in a new mechanism. And can you express this third axiom in that new mechanism? The third axiom in that new mechanism is going to be the probability of union of x values ranging from R1 to R2. Probability of x is equal to R1 union x is equal to all the values between R1 and R2 is equal to simply the sum of probability of x becoming any x value, and then I'm going to simply sum up all the probability mass function values. I hope you are not surprised. I hope you are not having any kind of scary feeling, because this is simply the three axioms revisited and the three axioms redefined. We are three axioms that we revisited, we studied in chapter number 1. We have simply revisited those three axioms. So now I'm not saying that you have become 100% master of this topic, but you understand now that what is a random variable? Random variable is a new language given to event. Random variable is a new name given to event. What is the probability mass function? Probability mass function is a function that generates probability values corresponding to different values of random variable, different values of random variable. And then when you say probability of an event can never be negative, when you say probability of an event can never be negative, it's another way of saying probability of x becoming any value can never be negative. When you say probability of whole sample space is 1, it's indirectly you're trying to say that probability of x becoming all possible values, x becoming any one of the all possible values is 100% sure. Random variable, if random variable takes any value, it will take at least one value. Any value it will take, at least one value it will take. Something will happen. That is sure. Something will happen. All right. If you cover all possible values of random variable between minus infinity to plus infinity, something will happen. And the union becomes the sum, becomes the sum, becomes the sum, becomes the sum. Similarly, the union becomes the sum. So three axioms that we studied in chapter number 1 have now been revisited. Now they are revisited. So once they are revisited, let's go ahead and try to verify that we already studied one distribution called geometric distribution. So let's verify axiom number 2 for geometric distribution. Does geometric distribution satisfy this axiom number 2? Let's verify that. So as a third problem, verify axiom 2 for geometric distribution. Geometric distribution is defined by geometric distribution is defined by probability mass function one minus a small p power x minus 1 multiplied by p. I want to verify the second axiom, and the second axiom says that the sum of all probability values will become 1. Why? Because something will happen. Out of all possibilities of a random variable, something will happen. Okay? If there is an event, there is a random experiment going on, something will happen. Now, let's try to verify whether if I sum up all the probability values defined by this probability mass function, are we really getting equal to 1? Let's try verifying that. So I'm going to get 1 minus p power x is equal to minus infinity to 0. It's nothing, because geometric distribution is defined only for x equal to 1. So naturally, we are going to break this between minus infinity to 0, all probability values, and then between 1 to plus infinity, all probability values. The first term becomes totally 0 because my probability mass function is not even defined for negative values here. So I cover only the values of probability mass functions ranging between x is equal to 1 up to x is equal to infinity. Now, I'm going to write x is equal to 1, and then I'm going to write x is equal to 2, and then I'm going to write x is equal to 3, and then I'm going to write x is equal to 4, and then I'm going to write x is equal to 5, and so on and so forth up to infinity. X is equal to 1, I get p simply. X is equal to 2, I get 1 minus p power 1 into p. X is equal to 3, I get 1 minus p square into p. X is equal to 4, I get 1 minus p cube into p. X is equal to 5, I get 1 minus p power 4 into p, so on and so forth, so on and so forth, so on and so forth. Keep going on. Now I can take 1 minus p whole common. So let us take 1 minus p whole common. Sorry, p whole common. I'm so sorry. If I take p whole common, then I have an infinite geometric progression inside. Do you notice that? And I hope all of you know what's the sum of an infinite geometric progression. So if I take p common, then I have 1 as the first term, 1 minus p as the second term, 1 minus p square as the third term, 1 minus p cube as the fourth term, 1 minus p power 5 as the fifth term, and so on and so forth. This is an infinite geometric progression. All of you know what is the sum? What is the formula of sum of an infinite geometric progression?
A by 1 minus r.
A upon 1 minus r. Exactly. So if there is an infinite geometric progression, ar square, ar cube, ar power 4, the sum of such an infinite geometric progression is given as a upon 1 minus r. You know that? Great. You don't know? Shame on you. geometric distribution is defined by PMF. Cool. So this becomes A upon 1 minus R. One and one get cancelled. I get finally what? Huh? I finally get what? I finally get 1. The axiom number 2 is now verified. We have successfully verified axiom number 2. Summation of all possible probability values is equal to 1. If tomorrow somebody comes to me and says that, look, I have found a probability mass function, comes with any random function, y is equal to e power x, or y is equal to e power minus x, or y is equal to sine x, or y is equal to cos x, or y is equal to tan x, and says, that person claims that this is defining a probability distribution. The first thing that I will do is to check axiom number 1, that is that function ever giving any negative value? If that function is ever giving any negative value, that can never qualify to become a probability mass function. That can never define a probability distribution. So probability distribution is a function, but not every function can become probability distribution. Probability distribution is expressed through a mathematical function, but not every mathematical function can become a probability distribution. Not every mathematical function can become a probability mass function. My dear friends, for example, if I define probability mass function by a function like this is an invalid PMF. Why? Because this can become negative. This sine x can become negative. I know that sine becomes negative after 90 degree, after x is equal to pi by 2, and up to, after between x is equal to pi and 2 pi, sine x becomes negative. So this can never play the role of a probability mass function. Second thing I'm going to check, even if first condition is satisfied, second thing I'm going to check is whether the sum of all possible probability values is becoming 1 finally or not. And if it is becoming 1, then I approve that yes, this is a good probability mass function. This can play the role of probability mass function, and we can get probability distribution values out of it. Cool. All right. Let's go ahead and start doing our next thing. So far, so good. While understanding probability distribution, we started with understanding what is a random variable. A random variable is a variable just like real variables in calculus, but its value is not fixed. A random variable is a variable whose value is not fixed, number 1. And number 2, whose value is not fixed, and number two, that it takes only numerical values, no characters. It takes only numerical values. It doesn't take any character ever. I mean, x can never become alpha, x can never become beta, x can never become head, x can never become tail, x can never become Lucknow, x can never become Kanpur, x can never become Hyderabad, x can never become Bangalore, x can become 2, 3, 2.5, 3.5, 2.92, 3.71, like that. Okay, so that's a random variable. And second thing that we did was to define the probability mass function. Probability mass function, saying it for one last time, probability mass function is like a machine. Probability mass function is like a machine in which you input the random variable values and you get the corresponding probability values as outputs. Random variable values are given as inputs and corresponding probability values are obtained as outputs, where the machine is what? The machine processing these inputs into these outputs. That machine is called by the name probability mass function. That machine is known by the name probability mass function. Dhyan se samajhiyo. And you know, one example we have taken, there we have expressed probability distribution or probability mass function in three different ways. One was in the form of a table, another was in the form of a histogram or a bar chart, and the third was expressing it as a mathematical relation. Probability of x becoming a small x is expressed as 1 minus p power x minus 1 multiplied by p. This is, of course, this thing we have done only for one specific case called geometric distribution. We have hundreds of such probability distributions defined. This is just one out of thousands of probability distributions that can be generated, that can be defined. Okay, and the third thing that we understood was the three axioms of probability, which we have studied very extensively in chapter number 1. So in chapter number 1, we have studied the three axioms very extensively. That first axiom was probability of an event can never become negative. The second axiom was that probability of whole sample space will be 1 because something will happen out of the whole sample space. And the third was probability of A union B is equal to probability of A plus probability of B. Probability of A plus probability of B. This axiom, my dear friends, in terms of our new language, this axiom is written as that the value of probability mass function can never become the value of probability mass function corresponding to any random variable value can never become negative. Second axiom is going to be expressed as that if we cover every single possibility of the random variable value, every single possibility of the random variable value, the total sum is going to be equal to 1. And the third axiom is going to become, the third axiom will be written like this, that if you are calculating the probability of unions of, if you are calculating the probability of the union of probability of different random variable values from R1 to R2, you simply sum up the probability mass function values corresponding to x is equal to R1 up to x is equal to R2. up to x is equal to R2. Great. Awesome. Three axioms redefined. Three axioms redefined. So suppose I give you a probability mass function and I just ask you that whether this is a valid probability mass function or not. What will you do? First thing that you will check is that the given function has only positive values possible. Second thing that you'll check is that if I sum up all possible values of that PMF, then the sum must be equal to 1. My dear friends, most of the times we are not interested in random variable becoming equal to 5, but we are interested in random variable up to 5. ध्यान से समझियो, बहुत ध्यान से समझियो. Most of the times we are not interested in random variable becoming 5, but we are actually interested in random variable taking any value up to 5, or random variable taking any value up to 10, or random variable taking any value up to 20, or random variable taking any value up to 50. Probability mass function gives you random probability corresponding to random variable becoming 1, becoming 2, becoming 3, becoming 5, becoming 10. But now we will be interested in not becoming 10, but random variable becoming up to 10. Okay? And that's going to be the next thing. We know how to calculate probability of x becoming anything, and this is called as probability mass function. Wait a moment.
చూస్తా ఉండండి.
Yes, so I'm so sorry. Probability mass function gives you the probability value corresponding to one random variable. But sometimes we are interested in not the probability value corresponding to one random variable, but corresponding to the random variable up to certain value. Okay. Let's take an example again. Because when we take a numerical example, we kind of comprehend more. We kind of understand it, in a way that we remember it forever. So let's take one example again. Let's repeat that example of salesperson only, that there is a salesperson and that salesperson is selling a product at a marketplace. There is a salesperson selling a product at a marketplace. So there is a marketplace where the salesperson is selling the product, and the probability of a person buying the product, the probability of a person buying probability of a person buying the product is given to us, and that probability of a person buying the product, let's say that probability is 0.18. Naturally, probability of a person not buying the product will be how much? Probability of a person not buying the product will be how much? Probability of a person not buying the product, 1 minus 0.18. Not buying the product, that will become 0.82. And now suppose I ask you the probability of getting a success, that means getting a product sold, the probability of getting a product sold in maximum 4 attempts. I ask you the probability of getting a product sold in maximum 4 attempts. This is our requirement. I hope you understood. So what is this required probability? How do we calculate it? First of all, we are going to change this whole problem in the language of random variable. So let's change this whole problem in the language of random variable. Let's define a random variable, number of attempts. Number of attempts I need to perform. Number of attempts I need to keep performing, keep pitching for our product till first person buys the product. Number of times I keep asking to the people till the first person buys the product. Okay, that becomes the random variable. Now, can you please transform this required probability in the language of random variable? I can transform this required probability in the language of random variable, that basically maximum 4 attempts. That means I can get success in 1 attempt, or I can get success in 2 attempts, or I can get success in 3 attempts, or I can get success in 4 attempts. I can get success in 1 attempt, I can get success in 2 attempts, I can get success in 3 attempts, I can get success in 4 attempts. All right. And in short, I can write, I want to calculate the probability of X becoming less than or equal to something. And now you realize that in many practical situations, we need probability value of not x becoming equal to something, but we need probability value of x becoming less than or equal to something. In many practical situations, we don't need the value of x becoming equal to something, but we rather need the value of x becoming less than or equal to something. Less than or equal to something. We need the probability of x becoming less than or equal to something. All right. So can you calculate that? Of course, we can calculate that. That will become probability of getting success in one attempt plus probability of getting success in second attempt plus probability of getting success in third attempt plus probability of getting success in fourth attempt. My dear friends, probability of getting success in very first attempt is 18%. Probability of getting success in second attempt means that the first attempt failed and I got success in the second attempt. Probability of getting success in third attempt means the first attempt failed and then the second attempt failed and I got success in the third attempt. Probability of getting success in the fourth attempt means the first attempt failed and then the second attempt again failed, the third attempt again failed, and the fourth attempt, I finally get the success. Now, since we are doing it up to 4, it is still manageable. But now suppose we have been doing it up to 40. Now suppose we would have been doing it up to 100. Now suppose we would have been doing it up to 1,000. It will become unmanageable. It will become unmanageable. We are doing it up to just 4 numbers, x is equal to 1, x is equal to 2, x is equal to 3, x is equal to 4. It is still manageable. But if we would be doing this same thing up to x is equal to 100, this will be an unmanageable calculation. 0.18 plus 0.82 into 0.18 plus 0.82 into 0.82 into 0.18 plus 0.82 into 0.82 into 0.82 into 0.18, 0.547878. People said that let's find a formula. Let's find a general formula that can give me the values of probability values of not x becoming equal to just x, but x becoming anything less than or equal to small x. Probability mass function is a function that gives the probability values of random variable becoming equal to any one value. Let's find out a new function that can give me the probability of random variable not becoming exactly equal to R, but let's find out a function that can give me the probability of random variable becoming any value less than or equal to R. This new function, my dear friends, that we are defining now, since it is adding all the probabilities from the start up to that value where we are interested. So we are basically finding out the accumulated effect and therefore cumulated effect. And therefore people started calling this new function that doesn't give the probability of x becoming equal to R, but it gives the probability of x becoming anything less than or equal to R. This new function is known by the name cumulative distribution function. And just in case if you think that what is the utility of such a function, what is so huge big utility of this function? Tell me if I want to find out the probability of x between 20 and tell me if I want to find out the probability of x x between 20 and 70, what will I do? What will I do? I will simply say that find out the probability of minus infinity, x being anywhere between minus infinity to 70, and then subtract from it the probability of x becoming anywhere between minus infinity and 19. My dear friends, all I need to do is I need to find out the cumulative distribution function value corresponding to 70, and I need to find out the cumulative distribution function value corresponding to 19. Cumulative distribution function is not represented by P, but cumulative distribution function is represented by capital F to avoid any confusion. Even though cumulative distribution function is also a probability generating function, but cumulative distribution function is not represented, not symbolized by capital P. Cumulative distribution function is symbolized by F. So when we write F70, we are actually trying to say that what is the probability of x becoming less than or equal to 70. And when we write F19, what we are trying to say is what is the probability of x becoming less than or equal to 19. This is a big utility if we can find a general expression of cumulative distribution function. So people said that if we are doing it for 4 terms, it is still manageable. We can add the things. Okay, done, no problem. But suppose if we would be doing this for 40 or 400 or 4,000, this would have become very unmanageable. This doing repeatedly 0.82 into 0.18, 0.82 into 0.82 into 0.18, 0.82 into 0.82 into 0.82 into 0.18, 0.82 into 0.82 into 0.82 into 0.82 into 0.18. Like that, doing again and again will become unmanageable. Let's better define a generalized function. Let's better find a general expression of calculating probability of x becoming any value up to x, and let's start calling it by a new name, CDF. And mind it, CDF is having more utility than PMF. PMF gives the probability corresponding to random variable becoming equal to one value. CDF gives the probability of random variable becoming any value up to certain value. And as I said, that suppose I define this random variable as the probability of, I define this cumulative distribution function as a second, let me just erase this. Hide video panel and save this. And bring the video panel again. All right. Now suppose in this scenario of salesperson or anything, Suppose I would have been interested in finding the probability of random variable being between. Suppose I would have been interested in I define this cumulative distribution function as probability of random variable becoming equal to or less than one certain value. What is the utility of this? Suppose in the salesperson problem, I want to know that what is the probability of that salesperson getting success between seventh customer and 30th customer. What is the probability that he's getting the success in from 7th customer up to 30th customer? So naturally, we are going to say calculate P7, calculate P8, calculate P9, calculate getting success in the 30th attempt. Now I have already P7 up to P30 available. I have everything from P7 and then P8 and up to P30 available. I have everything from P7 to P30 available. I introduce P1, P2, P3 up to P6. Naturally, I will have to subtract these values also. I will have to subtract these values P1, P2 and up to P6. Now, if you notice what this white shaded thing is representing, this white shaded thing is representing what? This white shaded thing is representing
1, sir.
the probability of, what does it represent?
1.
No, it doesn't represent 1. Are you covering all the possibilities between 1 and 30? You can get success in 31st attempt now. You can get success in 100th attempt maybe. Are you covering whole sample space? Whole sample space will go up to infinity. You did not cover the whole sample space. This P1 plus P2 plus P3 plus P6 plus P7 plus P8 plus P30 actually represents getting success in maximum 30 attempts. And if I take the minus sign common, then what does this remaining thing represent? If I take the minus sign common, then what does this remaining thing represent? This remaining thing represents probability of getting success in maximum 6 attempts. This is the very definition of cumulative distribution function. This is the very definition of cumulative distribution function. People said, if I define a new function called CDF that has the ability of giving probability values corresponding to random variable equal to something, no, that's PMF. Probability value for random variable becoming equal to something, that is probability mass function. Now we are searching for a new function that gives me the probability of X becoming any value up to certain value. That means I can write F2. F2 means what? F2 means simply probability of X up to maximum value 2. When I write F11, what does that mean? That means X1, X2, X3, X4, X5 up to X is equal to 11. When I write F19, what does it mean? F19 means I'm simply calculating the probability of random variable taking any value less than or equal to 19. Less than or equal to 19. So now I realize that finding such a function would have been such great thing. If such a function is known to me, I can simply put the value. Otherwise, finding this x less than 30 and x less than 6 is actually a laborious task. You want to do it without finding a function? Good luck. It's going to be really a laborious task. If you don't have a general function, it becomes a very hard working task. You can actually do this for the previous problem, getting success in one attempt, getting success in second attempt, getting success in third attempt, getting success in fourth attempt, getting success in fifth attempt, sixth attempt, seventh attempt, or getting success in 30th attempt, getting success in 30th attempt. Bapre. Summing up all these values in calculator is going to be a very cumbersome and tiring process. And then, of course, getting success in one attempt, getting success in second attempt, getting success in third attempt, keep summing up all the way up to getting success in sixth attempt. So this is 0.82 power 5 into 0.18 into 0.18. ध्यान से समझियो. If I can get any generalized function, I don't need to do this much monotonous calculation. So let's go ahead and find out the cumulative distribution function corresponding to geometric distribution. And that's going to be our next problem. As our next problem, let's try to find out find general expression of cumulative distribution function for geometric distribution defined by probability mass function one minus p power x minus 1 into p. So I'm now required to find out probability of x becoming equal to x? No. I'm now required to find out probability of x becoming anything less than or equal to x. So probability of x becoming anything less than or equal to x, that needs me to sum up probability of x becoming equal to 1 or probability of x becoming equal to 2 or probability of x becoming equal to 3 or probability of x becoming equal to 4 or probability of x becoming equal to 5 or probability of x becoming equal to or probability of x becoming equal to x. All right. So let's sum up all these things. If I sum up all these things, I'm going to have this one becoming 1 minus p power 0 into p, and this one becoming 1 minus p power 1 into p, and this one becoming 1 minus p power 1 minus p power 2 into p, and this one becoming 1 minus p power 1 minus p power x minus 1 multiplied by p. Cool. Now this is very clearly a geometric progression of how many terms? X terms. X terms or x minus 1 terms? Actually x terms. Why x terms? Because power starts from 0 and we go up to x minus 1. So 0 term and then x minus 1 term. We actually, up to 1, we have 2 terms. Up to 2, we have 3 terms. Similarly, up to x minus 1, we have x terms. If you know the sum formula of geometric progression up to n terms, great. If you don't know it from today. The summation formula of a geometric progression up to n number of terms is 1 minus r power n upon 1 minus r multiplied by a. 1 minus r power n upon 1 minus r multiplied by a. Naturally, p is common here, and 1 is the first term. 1 minus p is r. 1 minus p is square. Next term we have square, and next term we have cube, and finally we have 1 minus p power x minus 1. My dear friends, this is a geometric progression. So I'm going to get a into 1 minus 1 minus r power n upon 1 minus r. I get small p into 1 minus p power x. 1 minus p is playing the role of common ratio. And in denominator, I have 1 minus 1 plus p. 1 and 1 get cancelled. And after that, p and p get cancelled. After that, 1 and 1 get cancelled. After that, p and p get cancelled. Let me move it here. So next, I can cancel p and p. 1 minus p power x divided by p. P and p are going to get cancelled. Probability of x becoming anything equal to or less than small x, that will be given by 1 minus p power x. This is the cumulative distribution function of geometric distribution. Go back to problem number 4 and verify that are you getting x less than 4 thing, exactly the same final numerical result that you got by ordinary analysis. Go back to problem number 4, just previous problem that we have solved, and try to verify that are you really getting the matching results. Go back to problem number 4. The salesperson problem, and tell me what was the value of x less than or equal to 4 we found there. Somebody please tell me. What was the value we obtained?
0.54.
0.54.
0.547.
547. Can you verify here? One minus 0.18 power 4. Zero 0.547878. CDF
Yes,
is
sir. Exactly.
practically exactly same. CDF is practically a very beautiful thing that can keep giving you the probability values up to random variable getting up to certain value. Thank you so very much. We call it a day. Tomorrow we are going to do a very beautiful distribution, and that distribution is binomial distribution. That's also a very important distribution, not only a beautiful one. You are going to enjoy it like anything, believe me. So tomorrow we'll meet again with binomial distribution. Tomorrow, of course, we are going to have multiple classes, and in all probability, we have a high probability of finishing probability distributions tomorrow. We have a very high probability of finishing probability distributions tomorrow. All right. So I'll set
sir.
for new subject being started in the next week.